Good morning everyone. So yesterday we studied about the speed time curve and the various types of services available in the traction system. So today we are going to discuss about the speed time curve for different services. As we have discussed, there are three types of services, that is urban or city service, suburban, and the third one is mainline. So these are the relatively different type of graph that we can discuss on the type of services. So first we will discuss about the urban services. In the urban services you can see this type of graph as it is linearly accelerating, and at this point it will degrade and the coasting period will start, and after coasting the braking region will be available. So this shows the urban or city services where relatively value of acceleration and retardation are high in this region to achieve moderate high average speed between the two stops. Due to the distance between the stops, there is no possibility for free run in this region. Through it has a shortening coasting period that includes the saving energy consumption. Next we will talk about the suburban area. Alright, so as you can see, it is similar to that urban area, as the distance between the two of these graph is not so much, so the accelerating high speed will be as equivalent as compared to the urban, and the coasting region will be equivalent, and the braking too will be equivalent. What the difference is that the distance between the accelerating and deaccelerating, the rate of accelerating and deaccelerating varies. Now that third one we will discuss about the main line. In this main line we can see everything clearly, that is acceleration period, free run period, coasting and braking. So in this region, this service is available for long period for free run at present at high speed, and the acceleration and retardation are more important, as the rate of acceleration and retardation are slow because this is applicable for long period. Next we talk about the different type of speed. The first speed is crest speed. It is the maximum speed that a vehicle can attain during the running period, while it is running. Next speed is average speed. The average speed is the ratio of total distance covered between the two stops divided by the actual time that the train has taken between the two stations. The third one is scheduled speed. The scheduled speed is the ratio of distance covered by the train between the two stations divided by the actual time plus the stoppage time, means where the train has been stopped between the stations. So for example, if a train reaches 2 minutes later, 2 minutes earlier, then the scheduled time will increase or decrease according to the stoppage time. So as we can see always that the average speed is always greater than the scheduled speed in case of main line, but in case of urban city and suburban cases, this speed might get decreased. The scheduled time may get increased as compared to average speed. Now we will talk about the simplified speed curve. As we can see in the previous diagram, that the area under the curve tells us the distance, what the distance was traveled by the train in the given time of period, and we can calculate the crest speed, average speed and the scheduled speed from that area covered by that speed. And second point, that we can calculate the rate of acceleration and deacceleration with the help of this slopes. So what we are going to do with this region, we can calculate the total distance covered area. So for example, my train is accelerating at a constant in speed, and after some time that free run time come up, and after coasting it came to braking. Okay, so I can calculate the total amount of distance covered by this area. Okay, and accordingly I can shift all those points according to these points. Okay, so I have just marked down these points by this dotted line, and I have just changed the curve. I have just down towards it and moved the upward points towards this, so the total distance calculated remains same, the total work done will remain same. What will change? The highest accelerating point will change according to the load of the train. Alright, and this is the example of trapezoidal shape acceleration. In this we can see the acceleration, then there is a free time run up, there is braking and a coasting period at this end of this curve. So this is how I can equal the distance by equating the graph, by equating the total distance covered by the train in all of the cases. Coming to the main and final topic of the day, that is trapezoidal speed time curve. This, as you can see here, there is a trapezoidal shape, and you can see there is a point O, A, B, C, D, E, right? And there is time given by t1, t2, t3, and total time is t. This is the maximum speed that can be attained by the train, that is a Vm. Alright, so from A to O the train will accelerate from O to A region, and from in region A to B it will fall into free run category, and after B to C it will retards. Okay, so braking region is applied in this portion. So t1 is the accelerating time, t2 is free running time, and t3 is a retardation time, and t is the total sum of time of t1, t2, and t3. Okay, so let us get through all of these details. So d is the total distance covered by the train, t is the actual time that train will take between the two stops, alpha is the acceleration during the starting, beta is the retardation of the train, Vm, as I told you, is the maximum speed, and Va is the average speed, as we have discussed earlier. And T1 is the time accelerating time, T2 is free run up time, and T3 is the braking time. So what we can say, that total time is equals to like T, total T is equals to T1 plus T2 T plus T3. So what I'm doing right now here, I'm taking out the value of T2, that is equals to T minus T1 plus T3. Alright, so as I know that accelerating constant, as I have discussed, as I have mentioned here, alpha, which will be equal to Vm upon t1, because t1 is the time of acceleration. Alright, so I have used here t1. So I have to find out the value of t1. So here I just find out the value of t1 by moving all these constants. So t1 is equals to Vm upon alpha. Similarly, I have to find out the value of beta. Alright, so beta is, as you can see, retardation during braking region, and this region between B and C, that's the value of beta. Beta is equals to similarly like alpha, like Vm upon t3, as t3 is the time duration of braking or retardation. So t3 is equals to Vm upon beta. Alright, so what I have to find in this, I have to find this total distance in this trapezoidal shape. So total distance d is equals to area of this O, A, B, C, O. Alright, so this is the total area what I have to find. So the total area, as you can see here, which will be which is the sum of a rectangle and two triangles, that is O, A, D, O, A, B, E, D, and B, C, E. Alright, so I have just mentioned them down here. Alright, so the first triangle is O, A, D, second one rectangle A, B, E, D, and the third one is B, C, F. So B, C, E, I'm sorry. So alright, so the triangle area of triangle is equals to half Vm T1. This is the area of this rectangle, and again this triangle. So what I'm doing right now, I'm taking Vm as common from all the terms, and what I will left with this is T1 by 2 plus T minus T1 minus T3 plus T3 by 2. Alright, so again I'm taking out the T and most of the common in the bracket section. So what I'll be left with, I will be lefting with Vm is equals to T minus half T1 plus T3. Alright, as I have mentioned earlier, like T can be represented, T1 and T3 can be replaced with the terms, this one T1 can be replaced by Vm upon alpha, and T3 can be replaced by V3 upon beta. So what I'm doing right now, I'm replacing T1 and T3 and T3 in this section, and what I'll be getting, let us check. So I'll be getting those values, and I have assumed that value will be equal to k. So I have assumed that k is equals to half 1 upon alpha plus 1 upon beta. So taking the LCM of this, I'll get this k is equals to alpha plus beta whole upon 2 alpha plus beta. Alright, so this is the total value of k. Now jumping upon the previous equation, I got d is equals to Vm t minus kv. Alright, what I have done, I have just put it down the value of k in the whole equation, and I got this. Alright, so multiplying the Vm with the T and KVM, I got KVM square minus VMT plus D is equals to 0. So what I'm doing right now, I have to find out the value of Vm over here. So Vm is equals to what is simplified, as I've simplified it, that will become T plus minus T square minus 4KD upon 2K. So what will be the consequences here if I take the positive sign? So it will be much more than the practical value. So for the practical value, I am taking the negative sign over here. So the final value of Vm, that the maximum speed that the train can attain during the running, would be T minus T square minus 4KD upon 2K. Alright, And jumping upon the previous equation once again, as we have written here, that is k vm square is equals to vm t minus d. Alright, so let's find out the value of k, as we have mentioned it earlier, that k is equals to half 1 upon alpha plus 1 upon beta. So let's jump upon the value of k once again previously. So we'll find that k is equals to I'm sending this vm square upon this whole term, so I'll get k is equals to tm upon v minus d upon vm square. Alright, so according to this, what I'm taking common, I'm taking d upon vm square common from these terms, and I'll get this term. Alright, and the basic thing, as I know that speed is equals to distance upon time, and I'm making the utilization of this formula, and I'll put this formula over here, over in this section, and I'll get the value of k is equals to d upon vm square bracket vm upon va minus 1. So I get this value over here, va is equals to this, and I finally got out to reach out this formula where I can associate, where I can logically link the value of alpha and beta with the maximum speed that the train can attain. So I'll get this formula, that is 1 upon alpha plus 1 upon beta is equals to 2d upon vm square bracket vm upon va minus 1. So that's the whole thing what I wanted to teach you.